Welcome. My name is Mason Marchildon. I'm an engineer and hydrologist with the Oak Ridges Marine Groundwater Program. We are a small, arm's-length public agency funded by the regions of Halton, York, Peel, Durham, and the City of Toronto. Please enjoy my presentation. So today's presentation is titled Groundwater Discharge to Lake Ontario. This project was funded by the MOECP, who recognized that we were well suited to take a high-level look at loadings to the northern shore of Lake Ontario based on the data and the collection of numerical models we have in our archive. Today's presentation will be given in 3 parts. First, I'll speak to the data, in particular stream flow, and how we could use that to get a sense of the magnitude of water being discharged into the lake. Next, we'll look at numerical models that hopefully corroborate the data, but also use them to gain additional insights, such as the origins of the water that is entering the lake. And given that information, we can do a back-of-the-envelope quick assessment of the potential chloride loading that's getting into the lake via the groundwater system. Before proceeding, I'd like to go over some terminology that I'll be using frequently throughout this presentation. The first is the concept of slow flow versus quick flow. Slow flow being that signature of the hydrograph that is not apparently related to any direct contribution from a runoff event, such as a rainfall or snowmelt event. From the hydrograph's perspective, this is when the hydrograph starts to recede at the rate defined by its recession curve. Most hydrographs have a well-defined recession curve that is indicative of the hydrology of its watershed. Next, we'll turn to the perspective of Lake Ontario and the concept of direct and indirect contributions. Direct being along the shoreline, where groundwater is directly contributing to the lake, and indirect is the pickup of groundwater that occurs along its tributaries that eventually make it to the lake. Now, I've provided 4 definitions: slow flow, quick flow, direct, and indirect. For the sake of this presentation, slow flow and indirect are equivalent. It just depends on the perspective of what I'm speaking to, whether it's discharge to Lake Ontario or whether it's discharge along a stream. Now, indirect slow flow in itself carries some baggage. It's not to say that slow flow is indicative of any particular phenomenon, rather a set of phenomena that occur after that direct, quick flow runoff portion of the hydrograph dissipates. So, for instance, Van Meter et al., shown here, shows, for instance, that concentration and discharge are not necessarily in phase. And this could be attributed to other slow flow phenomena, such as superficial storage, like wetlands or stormwater management facilities, or infiltration into urban infrastructure, some call urban karst. And I take this to be a bit of a shallow water phenomena. And here we're going to neglect the seasonal shallow water phenomena and really hone in on the deeper system, long-term average phenomena. Good. So moving on to the data. In this figure, you first see the contributing area to the north shore of Lake Ontario in this gray hashed line. Within this area, you see a number of pie charts. Each of these pie charts are located at a streamflow gauging station with greater than 10 years of data. The size or radius of the pies are indicative of the total discharge measured at those points, whereas the pies themselves indicate the proportion of quick flow versus slow flow as per automated hydrograph separation routines. Each of these stations have metadata associated with them in terms of the name of the station, period of record, the quality of the data, drainage area, discharge, base flow index, and its streamflow recession coefficient. But rather than poking around at individual stations, I'd like to look at this as a whole. And what you'll notice at first is that the size of the hydrographs, or the total discharge, tends to increase the more urbanized the watersheds tend to be, which makes sense. I mean, that's intuitive. What we're also seeing is that the proportion of quick flow tend to increase in urbanized areas, which is also expected. But what's interesting is that the proportion of quick flow that increases also matches that total flow. And so that slow flow portion, in terms of sheer quantity, tends to be rather similar across the board. To illustrate that, the histogram on the left show the distribution of slow flow discharge according to all those plots. And what we see is that we have roughly 200 millimeters a year, plus or minus 100, of discharge moving into the lakes. Right? On the right-hand side, I added an additional histogram that illustrates the base flow index. That's the proportion of slow flow to total flow. And what this is seemingly telling us is that the majority of stations see that a greater proportion of its total flow is in that slow flow regime. Good. So moving on to numerical modeling, here's a map of a number of models that exist within our custodianship program. They are all quote-unquote regional in extent, but as you will see, the aerial coverage of these models vary greatly. So for instance, the two larger models are models offered with thanks from Aquantia and the GSC. These are integrated transient hydrogeosphere models. As you click on these layers, you could get a lot of information in terms of the complexity of the model. And as we zoom in, we could see what is common with all these models that have been selected for this study is that they all share a common boundary along the Lake Ontario shoreline. After running all these models to obtain long-term estimates of groundwater recharge versus groundwater discharge, we start to see that, in general, these models behave quite similarly. They're all around that 200 millimeter ballpark that we established earlier with data. They are all a bit on the lower end between that 100 and 200 millimeters, which is indicative of slow flow not being entirely composed of groundwater discharge. They could be from the wetlands and stormwater ponds that I spoke to earlier. But more importantly is we see from 1 to 5 to 10, maybe 20% of that groundwater discharge is coming from direct sources, so along that shoreline. So good. Now we can move on to our chloride loading estimates. So we know we have a 7,000 square kilometer contributing area. Let's assume that 200 plus or minus 100 millimeters of indirect loading is occurring, and then an additional 10% of those loading come from direct sources. I'll also reiterate from above that those out-of-phase pulses are a shallow groundwater phenomenon, and that we're only really considering the deeper system that provides a continuous long-term discharge. So I was lucky to be handed this paper by Mackey et al. Because it was a review of past studies looking at deep groundwater concentrations within our study area. And what we could see is that they all seem to hover around that 250 milligrams per liter. So let's use that. So if we estimate loading with a 7,000 kilometer drainage area, let's be conservative and pick 150 millimeters of discharge, both direct and indirect, and a 250 milligram per liter chloride concentration. This equates to 260,000 metric tons per year of chloride being injected into the lake from deep groundwater sources. This amounts to 26,000 tons per year of direct discharge along the shoreline, and the remaining being indirect, if we take the information from the models. But how does this relate to road salt application? In an attempt to backcheck these estimates, we had approached Environment and Climate Change Canada, and we had retrieved a database of road salt application rates reported by municipalities over the last 10 years. When we look at the distribution of these application rates, we could say there's roughly 10 tons of road salt applied per kilometer of serviceable road. So let's put that back into our estimates. Given that there's 25,000 kilometers in total length of road within our study area, this 10 ton per kilometer per year application rate amounts to 25,000 tons per year of salt applied in the region. And when we look at these two numbers and compare the two, we could see that no matter how conservative or whatever estimates I applied here, we are in the same ballpark. So as a conclusion to this presentation is that the contribution of chloride to the lakes from groundwater sources is significant and may even be more so significant than the salt loading occurring from a runoff event. And I'll leave it there. Thank you for listening to my presentation. I look forward to your questions.